Welcome to the deep dive. Today we're looking at something critical if you're dealing with water systems, especially complex ones, maybe like those you're studying in India. Poor and polyfluoroalkyl substances, PFAS.
That's right. They're sort of fundamental to modern life in many ways, but their very nature creates a huge challenge for water quality.
Exactly. So our mission today, let's unpack what PFAS are, how they got everywhere, and why they're so incredibly persistent.
Okay, first thing to grasp is the scale. PFAS isn't just one thing. It's a massive family of chemicals. Over 38,000 synthetic compounds.
38,000. Wow. But they must share something in common.
They do. The defining feature is the carbon-fluorine bond, the CM bond. It's exceptionally strong.
And that strong CF bond.
Yeah.
That's really the heart of the matter, isn't it? What does that strength mean in practical terms?
It means they're incredibly resistant. Resistant to heat, chemicals, water, oil, grease, you name it. And crucially, resistant to breaking down in the environment.
Ah, so that's where the nickname comes from. Forever chemicals.
Precisely. That bond strength means they just don't degrade easily through natural chemical or biological processes. They persist for a very, very long time.
Okay, persistence is key. But their usefulness must be why they became so widespread. How did they end up in, well, everything?
Their unique properties made them incredibly useful. Think about non-stick coatings.
Like Teflon.
Exactly. Teflon, that was a big early one. But then it moved into water-repellent fabrics for clothing and outdoors, stain-resistant carpets.
And food packaging, too, I remember reading. Like grease-proof paper.
Yes, that kind of thing. Microwave popcorn bags are a classic example. Anywhere you needed something to resist oil or water.
But one use stands out, particularly concerning for water sources near airports or military sites, the firefighting foams.
Absolutely. AFF, aqueous film-forming foam, hugely effective for certain types of fires, but used extensively for decades, especially at training sites.
And when those foams are used, or when industrial sites release wastewater, those become point sources, right?
Yeah.
Potentially high concentrations.
Definitely point sources. Industrial discharges, say from textile manufacturing or chemical plants, can release PFAS at levels like 100 up to even 10,000 nanograms per liter. Very concentrated.
But it's not just those big obvious sources. There are diffuse sources, too, which sound maybe harder to pin down.
That's a major challenge, especially for managing water quality broadly. Think about consumer products ending up in landfills. The PFAS can leach out over time.
And wastewater treatment plants, do they remove PFAS?
Well, that's the problem. Conventional wastewater treatment isn't really designed for these chemicals. It's often ineffective at removing PFAS or even their precursors, which can then transform into PFAS later. So they often pass right through and into rivers or lakes.
So you've got persistence, widespread use, and ineffective removal, meaning these chemicals are now basically everywhere, global distribution.
That's what the evidence shows. They're highly mobile in water, they don't break down, so they travel far.
How far are we talking?
Startlingly far. PFAS have been found in rainwater samples collected all around the globe, even in remote areas far from any obvious industrial source or population center. It shows they can travel through the atmosphere and deposit anywhere.
Wow. Okay, so it's a global contamination issue. Let's connect this to the bigger picture then, the biological side. What about risks to living organisms? Bioaccumulation.
Yes, that's a key concern, especially for certain types of PFAS, like the longer chain ones, think PFCAs with 9 to 14 carbons and PFOS.
They build up in organisms.
They do. They bioaccumulate. And not only that, they can biomagnify, meaning the concentration increases as you move up the food web.
And I've read something interesting. They don't accumulate in the way we usually think about contaminants, like in fat tissue.
That's a really important distinction, particularly for PFOS. Unlike many other persistent pollutants that dissolve in fats or lipids, PFOS tends to bind to proteins within the organism, like in the blood or liver of fish.
So it behaves differently in the body.
Exactly. It changes where it concentrates and how it moves through the food chain. It's not quite the same mechanism as, say, DDT or PCBs.
Okay, so let's try and summarize. We've got this huge class of chemicals defined by that super strong CF bond, making them forever chemicals.
Right. Their useful properties led to them being used everywhere, from cookware to firefighting foam.
Which means they get into the environment through industry, product use, landfills, wastewater.
And because they don't break down and travel easily, they're now found globally, even in rainwater.
And they build up in living things, sometimes binding to proteins, moving up the food chain. So what does this all mean, really?
It means their stability is both a blessing for industry and, a curse for the environment. We're stuck with the contamination that's already out there for a very long time.
Decades, perhaps longer. So here's the final thought for you to consider. If these chemicals can stick around for years, even inside the human body, what's the real ultimate cost, socially, environmentally, economically, of creating something designed never to disappear?